Good morning, everybody. Welcome to today's training on creating data processing services. It is going to be quite an interesting session, and we have several different speakers, so we're sure you're going to enjoy it and learn a lot. And I'll let Juanjo introduce the session. Oh, I don't know why he's not on the stage, so I'm inviting him to the stage.
Okay, so now I guess you can hear me, right?
Yes, we can.
Okay, so good morning, everyone. So we are going to have this session, which will be focused on AI services and how you could integrate, for instance, and create experiments where one of the components might be that of adding participants that might be AI service providers. One thing I want to clarify, and this applies to the session we had yesterday, where Jason was introducing a number of components that could be helpful for integrating with IoT devices and so on. Today, we are also going to give some examples how to develop AI and machine learning services. But these elements, components we will see today, components we saw yesterday, are not as such part of the I4Trust framework. However, we wanted to give an introduction to them because it might be helpful how you may develop some experiments and how to be able to develop some of the elements in the back end of participants that could be useful for creating the kind of services and applications that participants in a data space enabled by I4Trust could use. Let me start sharing my screen, and this way my presentation, but give me just all right, so let me be sharing the screen. Yeah. Screen. Yeah, just tell me when you see my screen.
We can see your screen.
All right. So this was a bit, you may remember, one of a very high-level view of what we are trying to do and what we are enabling through I4Trust. We have we may have a data space involving several participants. I may have on one side a smart city, on the other side, like systems linked to a smart building and a smart port, and these actors might be exchanging digital twin data using NGS-ILD, leveraging on I4Trust security framework that complies with the iShare scheme. No? And for instance, we may have scenarios where the smart port might be using information about that the smart city might be exporting to, for instance, be able to determine what is the best moment to allow the traffic of trucks going out of the port or entering the port. Could be more efficiently managed, taking into account the traffic of the city and stuff like that. How smart buildings may leverage on information as well of the city and the other way around, and so on. That is kind of a scenarios that you may think about looking towards experiments. But another kind of scenarios are scenarios where what we may have as participants in the data space are providers of services that are kind of plug and play services that will be useful to extend the systems that a given participant may have in place. So just to illustrate this with an example, I may have a smart city that has been could have been developed using fiber. By the way, that's very is starting to be common in cities in Europe and so on. Well, that city might be measuring traffic in the streets, but they would like to extend their traffic management systems with powerful traffic prediction services. But those traffic prediction services might be based on artificial intelligence, machine learning algorithms that are able to exploit information not only about the traffic that is measured in a given street, but also information about weather forecast and events in the city, a number of things that all together based on AI, advanced AI techniques and so on, would be able to allow me to predict the traffic in a street. And there might be a what we want to enable, and we would be able to enable through I4Trust data spaces, is that such kind of AI service providers would be able to emerge, make their offering available so that other participants, instead of developing these sophisticated AI services, and they may not have the people with the skills and know-how on AI necessary to develop such services, what they would like to do is just extend their architecture by means of plug-in and play those AI services that third parties might be providing. So we may have a scenario like this. We may have a smart city that has already an architecture that is based on digital twins, based on fiber, and that city may wish to extend its architecture by means of adding a traffic prediction service a third party is offering. That traffic prediction service may, on the other hand, in turn, rely on a weather forecast service provided by another party, like a meteorological service. And I may have also a smart packet delivery company, which wants to rely on data that the city is exporting, not only about the current traffic, but also the predicted traffic, okay? So these are kind of scenarios we would like to enable, where, as you see, essentially, if I consider this kind of AI service I'm representing on top, this traffic prediction service, what we are doing is that we are standardizing the way such kind of services would be interfaced. How you would inject the data, how you obtain the results. Indeed, if we think about the essence of the interface of any kind of data processing service, you may start with this very basic vision. We have a consumer application. That consumer application will be injecting data into the data processing service, and that data processing service is generating results. And all this is happening in a constant a stream of stream flow. So data injected in near real time as data is injected, results being generated. And AI services are not very much different than that. It's a particular case of data processing service. And what we want to do, and one of the things I4Trust would be able to support is this ability to integrate and in the architecture of an existing consumer application a number of data processing services, some of which might be AI services. And for this to happen, what we are doing is simply making it as simple as building a Lego construction. And Lego works because what we are doing is essentially leveraging a number of standards. Each piece in the Lego buildings have these elements with concrete shape, width, height, and because this is kind of a standard for all Lego pieces, those Lego pieces can be integrated. So what we want to do is to apply this Lego principle in integrating both consumer applications and AI services. And these standards that make these pieces be plug and play are essentially the same way we had these 3 dimensions in the Lego pieces. We have these 3 dimensions, which is what we are standardizing in I4Trust. Common security framework, a common data exchange integration API, and common data models. So in the particular case of I4Trust, we are talking about the ICR scheme as the security framework. We have been, you have seen during the different training sessions that this is basically supported through the combination of a number of components like Keyrog and AP Umbrella, implemented in Fireware and aligned with Fireware, iShare specification, and as well iShare satellite services. On the other hand, we have the NGS-ILD API as the basic exchange data exchange API, and we have standardized data models. And this is what would allow you to create pluggable AI services. What is the vision when combined with the marketplace services that also are part of the I4Trust framework? The idea that some of these AI services would be offered through the marketplace, and then consumer applications will be able to pick and select those AI services, be able to activate them by means of acquiring the access rights to use those services. Same way we were seeing in the initial use case the other day with the packet delivery service company, and this way be able to adapt. What we are going to see today is, well, if we go through a little bit on the details of how these AI services might be architected, we typically may have an architecture. If we were not decoupling the AI service from the original application, if everything had been developed all together, we would have an architecture like this, and for instance, applicable here to a particular use case, which might be predicting animal fatting. No, I may be having a system that is on one side measuring the weight of each animal, and on the other hand, provided information about the diet of those animals. And through AI algorithms, what I'm intending is to predict not only the current weight, the current weight is being measured, not only the weight in 10 days, but also end of the seasons. So what you would typically do would be training those algorithms during a first phase, of course, because you need to select the particular models that you would apply. But once those models have been trained, what you would have is an architecture like this, where on one side you would be measuring or gathering input data, either coming from IoT agents or coming from different systems into the context broker, and this context broker delivering notifications to Spark-based systems. For instance, if we have selected a Spark and with its machine learning modules to support the kind of prediction service that we want to implement in this case. And what we need is to decouple this and be able to work in separate environments. On one side, having on the left the environment that typically the farm management system, which will be the consumer of those AI services, will have in place, which is the typical architecture where you have a context broker, where you are gathering data and exposing that data as input to the service. And on the other side, in the service provider environment, what we are going to have is, again, a context broker, which will be the context broker through which the AI service provider will be managing that view of the world they need to have access to in order to process data and perform the prediction. And the results coming out of that prediction would be exposed through the context broker that service provider should have deployed. And this way, through that context broker, the farm management system, which is the consumer application in this case, would be getting access to the results. So results would be exported as those attributes associated to an animal that correspond to the predicted weight in 10 days or in end of the season. And both systems, the farm management systems and the AI service provider, the animal predicting animal fatting service, what are doing is sharing this digital twin representation of the world, where certain attributes are being provided, are being fed by the farm management system, like the current weight of the animal, like the current diet of the animal. Other attributes are being provided by the AI service provider, the predicting animal fatting service provider, like the predicted weight in 10 days or the predicted weight in end of the season. Yeah, so essentially the vision is this, and what we are going to see today, and with this I finish, to give entrance to some colleagues from the Fireware community, what we are going, and also some people within the Fireware Foundation that has been working in development of such kind of frameworks. What we are going to present to you is a couple of examples of frameworks based on machine learning and AI that could be the kind of frameworks that in a given experiment someone might be proposing to be able to implement experiments where part of the experiment has to do with a participant playing the role of an AI service provider that integrates with potential consumers of its service through an I4 Trust data space. Today we will have two presentations besides after this one coming from a company within the fireware ecosystem called eGlobalMac. And eGlobalMac has developed a very interesting machine learning as a service framework that could be used for this kind of scenarios we are describing. After their presentation, we will have, by the way, since their presentation is long enough, a break in between. But after their presentation, we will have an additional presentation of a similar framework that is being developed in the context of another project. Altogether, what we try to bring here in the session today is ideas how advanced AI service, advanced machine learning service might be developed and might be developed with a vision how they could be integrated, how they could be consumed in a data space supported by the I4 Trust framework. And well, with this, I'm going to stop here and give first the floor to our colleagues from eGlobalMac, to whom I would like to thank and because they have volunteered to present the work they are doing, which is quite interesting. So whenever you are ready, Benoit, the floor is yours. Thank you.
Yes. Do you see my screen and the presentation?
You see your screen?
Yes. Okay. So hello everyone. So I'm Benoit Orihuela, working at EGM, a small IT company located in the south of France, and I'm more specifically involved in some fireware activities and mainly around our solution, which is called Stelio, which is a context broker implementing the NGS-ILD specification. And more recently, we start working a lot on machine learning activities inside fireware architecture and fireware ecosystem. And so today we'll talk about fluid machine learning lifecycle within a fireware architecture. As an introduction, what we are going to talk about this morning is an ongoing work in the context of a European project called Fireware for Water. And as its name implies, it's about water management activities. So it's still ongoing, but with the objective to easily deploy and use machine learning models. So before I describe in more details what will be showed later in the demonstration, let's refresh our minds on what it is a typical machine learning lifecycle. Usually, we have mainly 3 persons involved in such a lifecycle. First one is a data scientist, so he's the one that will get the data from a context broker or from other external third-party source. The data scientist will also typically clean up the do you see the slide with what I call typical ML lifecycle?
No, we are still on the PDF, which is not full screen.
Oh, Okay. Let me try to restart the sharing. Is it better now?
Not full screen, but we are on the
Yes, no.
slide number 3.
It's not full screen, but we do see your slide on a typical ML lifecycle. Now we lost your screen completely.
Yes, I am back.
Yes.
Yes. And do you see the typical ML lifecycle slide?
Yes, we do.
Okay, great. Sorry. So yes, a typical ML lifecycle involves mainly 3 persons. So first one is the data scientist, which will get data from a context broker or from an external third-party source. It can be open data or things like that. It will also typically have to clean up the data because we rarely have data which is totally cleaned. And it will prepare and train a machine learning model. For this, there are a lot of existing tools and frameworks. For instance, there are frameworks like TensorFlow, Keras, PyTorch, and so on, and a lot of tools like Jupyter Notebook to train a model and test it. Then we have an IT person, which will do some technical things, and mainly it will package and deploy the machine learning model that has been previously trained by the data scientist. And finally, we have an end user, which can be a client, typically a client. That will first have to discover the machine learning models that are available inside a context broker. Of course, with respect to security and privacy. And as Juanjo talked about it in his presentation, you can use the same existing tools that are typically used in the fireware architecture. And for that, what we have to know is that a machine learning model is just a typical NGSILD entity. So we can apply the same security rules and same privacy that for any other entity that is living inside an NGSILD context broker. Then the end user will ask to use one or more of the available machine learning models. So you are not restricted to use just one. You can choose among the available machine learning models. Optionally, you can of course pay for it because you can deploy your machine learning models on the fireware marketplace, either for free or asking for a fee. And then finally, you can use your machine learning model, one or more of the machine learning models that you want to use. You can use them in production in real time and start to get some predictions, outliers, or any processing that you can get from a machine learning model. So that are the 3 main persons involved in a typical machine learning life cycle. And in the current experiment work in progress we have in the context of a fireware for water project, we are aiming at two main things. First point is that we want to bridge the gap between data scientists and operations, because currently a data scientist has a lot of tools and frameworks to prepare and train its data model, but it often gets complicated when he wants to deploy a new machine learning model into production. So we want to bridge this gap and to give some autonomy to a data scientist to deploy any new machine learning model it has just trained. So this is what is typically called ML Ops. Second point is to develop the concept of machine learning as a service. And by machine learning as a service, we are on the end user side that can browse and discover machine learning models that are deployed inside the fireware architecture, and that can just issue some requests and start using any machine learning models in a few seconds. And this work is also driven by two other points. First, of course, as you may all know, there are more and more use cases requiring machine learning and artificial intelligence activities. So there is a real need to be able to benefit from a large variety of machine models and to be able to use them very easily. And also, fireware needs to offer a rich variety of tools. So we need to provide fireware with a lot of different ways to run and to exercise machine learning activities. So in more details on the different steps, so we have this first phase that we call training and preparation phase, which implies mainly the data scientist. So we have this data scientist that can get some data from a context broker, typically with some web application where it can export CSV data. It can also use a well-known fireware generic enabler, which is called Draco, which can easily be programmed to export CSV data from a context broker. Then the data scientist will use its usual tools to train and prepare a new machine learning model. And then it will package its machine learning model, and it will be able to publish it on some kind of registry. So it can be a Docker Hub, which is a well-known registry to deploy Docker images, or Yatai, which is a specific registry for machine learning models. And once the machine learning model is published on a registry, it just has to declare the machine learning model entity that is containing his machine learning model, and ask to a context broker to deploy it. And this is the fourth step, where the context broker will deploy the new machine learning model for everyone to be able to use it. And to do that, we use a tool framework which is called BentoML.
Sorry to interrupt you,
yes,
but we're still in the same slide. I believe you wanted to go forward.
You don't see the slide, the training and preparation phase?
No, we're still in a typical ML life cycle.
Okay. I don't know why the slide.
Yes, now we can see it.
Ah, now you can. Okay, so I just have to stop the full screen.
Well, we don't see you on full screen, actually. We only have you in the PDF.
And now you don't see the full screen.
Now we see a black screen.
Okay. So let's just. And now do you see the slide 5?
We see the slide, the training and preparation phase with a diagram.
Okay, and not in full screen.
Yes, that's correct.
Okay, so well, let's stick on this view because it seems that when I switch to full screen, you don't see the slide and they don't change. So I will stick on I will stay on this view.
Yes.
Maybe just click on the arrow to make the sidebar disappear. That's possible.
To click on what?
On the little arrow to make the sidebar disappear. On the right. Yeah. Yeah, perfect. Yeah.
Oh, okay. So I was explaining this training and preparation phase so quickly because I've just explained it. We have a data scientist which is getting some data from a context broker. Then training and preparing is it's a machine learning model. And then with the help of an IT person, it packages the machine learning model inside a Docker container. It publishes the Docker container either on Docker Hub or on Ngatai, which is a Docker registry specifically tailored for the machine learning else. And then it creates a machine learning model entity inside the context broker and asks for the context broker to deploy its newly prepared machine learning model. And for that, we use a framework called BentoML, whose main goal is to ease the runtime execution and runtime interaction with previously trained machine learning model. And we are currently working on adding an NGS-ILD wrapper around BentoML so that it can natively talk with any NGS-ILD context broker. And so once the training and preparation phase is done, and once the Docker container containing the newly trained machine learning model is deployed inside a fireware architecture, we have a second phase, which is called the discovery and registration phase. So in this phase, we have a new actor, which is the consumer application. So it can be any end user that want to use a given machine learning model. So that starts with a discovery. And the discovery is just about making a query on the context broker to ask for any known machine learning models. And when you get a machine learning model, you have some information about it. What is the framework that has been used to train the model? What is the algorithm which is used to run the model? What are the expected inputs? What is the format of the results, and so on. So you have all the information to decide on which model you are interested. When you have chosen an interesting machine learning model, you just have to register for a new processing. And in this processing, you are just saying, I want to use this machine learning model, and I want it to run when I update this specific data. So this is just about making a match between some input data and a machine learning model. And this input data will be then provided to the machine model as an input to the processing. When you do this registration, the machine learning model is notified about this registration of a new processing, and this notification is a standard NGS-ILD notification. So for that we used standardized subscription notification mechanism, which is part of the NGS-ILD specification. And upon the reception of this processing, the machine learning model will subscribe to the input data that is defined in the machine learning processing registration. And on the other side, the consumer application will subscribe to the results that will be later published by the machine learning models when we will do some processing on input data. And so this discovery and registration phase is done only once when you want to register a new processing on a given machine learning model. And then we have the third and final phase, which is the prediction phase, which is the interesting one when we will start getting some results, some predictions, for instance, from a machine learning model. So typically, we have some IoT agents, so some source of data that will update data of an entity in a context broker. So that will often be some sensor that will send a new measure that will be then transmitted in the context broker. The machine learning model, which has previously subscribed to input data, will be notified of the change, of the update of a new measure. It will use this input data to make a prediction. And when the prediction is ready, it will publish the results into an entity inside the context broker. And then finally, the consumer application, which has also previously subscribed to the results, will be notified of a new result that is coming in. And in real time, the consumer application will receive the new results from one or more machine learning models. Sorry. So this is the main flow that we have developed in the context of a FileWare for Water project, and so whose aim is to simplify and to have a fluid machine learning life cycle inside a FileWare architecture. So that's all for the introduction, and you will now have two demonstrations from my colleagues Didier and Anwar from EGM. The first demonstration will be an end-to-end demonstration of a ML model development, deployment, and use. So that will cover the three phases that I just talked about. And for that, it will use Jupyter Notebook to prepare and train and package a machine learning model, and also use sample web application to simulate the consumer application. And it will be applied to a simplistic water flow calculation. And then my colleague Anwar will demonstrate an event generation from a video stream analysis. So still using BentoML framework, but this time focusing on the real-time extraction of context information from a video stream. So that's all for me. I will now give the floor to my colleague Didier. Just stop sharing.
Okay, thank you, Benoit. Good morning. Everyone can hear me well?
Yes, we can.
Okay, excellent. So my name is Didier Dumais. I'm a data scientist at EGM. So let me share my screen first. Can you see my screen? Not yet. I do have a button saying stop sharing, so it is sharing somewhere. Okay, let me try again. Stop sharing. And share screen. Doesn't seem to.
No, we don't see your screen.
Yeah, it's going around. It's turning in a. Doesn't seem to. It doesn't seem to work. You're sharing. I just need to click on the share screen, right?
Yes.
Yeah, yes, at the bottom of the screen.
Yeah, but I'm doing it, but it doesn't seem to start.
Maybe try to reload the page. Don't know.
I think most of us, it's our first time using Hermit for these trainings. So it's always a little bit tricky, unfortunately.
Okay, Didier has an issue with Hermit, which is only providing a black screen, so he's trying to reconnect.
He's not coming back. I don't know how, if it would be possible, perhaps that Anwar presents now and then we come back to this part. I don't know if the order has to be strict or if it's flexible of presenting.
Okay, so Didier is still fighting with Hermit, who doesn't want to start again on his computer. So he's trying to solve the issue. So it's a bit less logical, but still we may move to the next presentation of Anwar, if Anwar is ready to go.
I think I'm back. Can you hear me?
Yes.
Yes.
Okay, so let me try again to share my screen. Share screen. Share.
Yes, we can see your full screen.
Excellent. Sorry for that. I don't know what happened. I was saying, my name is Didier Dumais. I'm a data scientist at EGM. And so what I will present you now is really what Benoit has presented on his slides, which is really demonstrating the IE service provider and the IE service consumer. So I will be switching a screen to different part of a demonstration and to show the different flows that we have. So I don't know if you can see correctly this flow for now, which is really what Benoit has demonstrated in his presentation, but on another view. So it shows the different actors of the demonstration and what everyone is doing. So we have on the left the data scientist and the IT person, and in the middle in blue, this is really the BentoML artificial intelligence model that will be running here.
It's and quite small. Would it be possible that you zoom in?
Yes, of course, of course.
Thank you.
Tell me when it is good. Is it better like this? It's fine?
If you can do one more?
One more, yes, sure.
That would be Yeah, that's perfect.
Okay.
Thank you.
Okay, no problem. So we have a context broker here, and the consumer app, and some IoT device that will simulate the update of some property into the context broker. So basically, what I will demonstrate is really an application that from an entity, a river entity stored into the context broker, use the precipitation information to predict the flow of this river based on the precipitation. So what we will do is really building a simple, very simple model for this kind of prediction, and deploy it as a Bento ML processing unit. So let me show you first the really what is the river entity looks like. So it's really a simple entity with two property. One is the flow, so what we will want to predict, and the second property is the precipitation. So that's something that is measured basically. So our IoT agent or sensor will update that part of the river entity, and that will basically trigger all the processing of making the prediction and so updating then the flow here of the entity. So what I will start to do is really that part as a first as a data scientist building that model. So I have prepared a Jupyter notebook that I will run through, and basically it's a really simple model, so a basic linear regression model, and I'm using a framework called scikit-learn. I don't know if anyone is familiar with that, but it's a very popular framework for different algorithms. And what we will do then is basically, I'm running a notebook. So I have downloaded already from the broker some historical information of the river. So the two parts of information, the precipitation. So that's the raw information that we get when we download it from the context broker. So I'm just doing some a little bit of cleaning and on the data just to make it more presentable and usable for the machine learning. So here, yes, you can see that we have for the precipitation, we have a date at the precipitation and the value of the precipitation. So it's in millimeter. So yes, we're living in a very sunny area. So yeah, there is a lot of zero precipitation. I'm doing the same for the flow so it's historical data here of the river. So again, some basic preparation of the data, and let's display a bit what we have as data. So what I'm displaying here is basically the flow as a function of the precipitation. So we can see that it does not necessarily depend on the precipitation because, of course, of a delay in the flow of the river. But again, it's simply a simple model to demonstrate the Bento-ML capacity. So what I'm doing here is now basically doing the prediction using the scikit-learn framework. So as an input data, we'll have the precipitation, and what we want to predict is the flow. So that will be our Y data. So I'm fitting a linear regression here. I'm doing the prediction of all the data that I have downloaded, just to show what the prediction will look like. So that's the red part. So it's a straight line. It's a linear regression. So of course it's not the best model ever, but again, it's just for the demonstration. And the important part here is I'm saving the model. So I'm saving the model as a pickle here, and this model is what we will package into Bento-ML, and that will then be deployed. So now the next part here is about, so I did this part about building the model. Now we will look at the part of the IT person deploying the model into Bento-ML. So I forgot one part, which is one step for the data scientist is basically packaging the model using Bento-ML. So that's really easy from a Bento-ML perspective. It's really a two Python script to write. So one is really this flow prediction is really about defining the environment that are required for the model that you have built, and then defining a class from the Bento service class, a main class, defining what are the type of input and output that the model is expecting and will produce. And
Didier,
yes.
Can you increase the?
Sorry. Yes, I can. Better now, yeah.
Yes, seems good.
Okay. So really about again creating this test flow model. So your prediction model, specifying what will be the input, the type of input, and the output, and defining this predict function. So in our case, it's simply a very simple predict from one data, which is the precipitation. And then the second script is really about the Bento-ML deployment part, which is we use our model that we just said, and we package it with the Bento-ML service, and we save the service. And so I will demonstrate actually what is going to do. So there is one script, only one script that we need to run actually is this one that will do the packaging into the Bento-ML. So okay, I'm increasing the size again then here. Okay. So I prepare the command so that we are quicker. So it's again just running the script, and what will happen here is Bento-ML will package all this information that our model that we created into one Bento-ML, so into one package. So there is a lot of very well described in the documentation, a lot of command line interface with Bento-ML. So for instance, I can list all the model that I created, and we should see our model here created like 30 seconds ago. So this model has been created and is ready to be deployed. One way of deploying this model is really to create a Docker with it. So for this, again, there is a simple command that we can issue. What I'm doing here is getting the path of the last model I just created. And then it's just a matter of doing a Docker build with this model. So let's create a V2. And so then Ubuntu-ML will create these two models. So if list the images that I have, so this is the newly created model created just now. So now that we have this Docker, it's just a matter of deploying it. So what we have done is because here I'm local on my machine, it won't work. The overall demonstration that we have done won't work with that Docker, but we have deployed before the call the same kind of Docker on another machine, so I can continue the demo with this. So basically, what we have deployed in another host is really the same Docker, the same content of what I've showed you just now. So here, what we say is we did that part, and the next part is for the IT person to create into the context broker this ML model entity. So for this, I will use another Jupyter notebook that just do that, the creation of a ML model. So I can show you the here you can see how the ML model is defined. So it's really an entity of type ML model, and we have some, as Benoit was mentioning during his presentation, some property for this model that can be used for the discovery of the model. So here again, it's a linear regression algorithm, and we are using precipitation to predict a flow of the river Sian. So I'm creating this into. So I'm sending a create request to the context broker, to our context broker. Just checking that this has been created. Yes, put it here. And now the next step. So I just did that one, number 2. So the next step is to create a subscription to the any ML processing entity that will register to that ML model. So that the ML model entity will be notified when, I mean, our model will be notified when the ML processing entity will try to use this this model. So I'm doing the second step here. And again, this subscription is about so it's an entity of type subscription. Subscribe to so the ML model will subscribe to any ML processing entity that will be interested into this particular model. And we specify here the endpoint where to receive the notification for this. So creating this. Okay. So the next step. So here everything is ready from the ML model perspective. Is basically a way some consumer application to create an entity. So mentioning that he wants to be using this service. So that part is here. So the consumer app will have to do three things. So create a subscription query entity, and that is to basically tell the ML model where he will be able to find the input data. And then this consumer application will create an ML processing entity. And this ML processing entity will contain a reference to the subscription query, so that the ML model can get to it. And so what will happen, obviously, is whenever as soon as this ML processing entity will be created, a notification will be sent to the ML model. So that will be the step 7. The third part that the consumer application needs to do is really to create a subscription to the prediction. So obviously, the consumer app wants to be informed of any new prediction. That's basically the goal. So we have a consumer app that actually will do the 3 steps in a row. So I'm opening the, so let me try to zoom again here. Up. So again, clicking on Create ML Processing will execute the 3 steps that I've been describing earlier. Okay, so the 3 entities have been discussed have been created. So, oops. So the app is basically just going to the result, a kind of result page, just to show the result of a prediction. So the prediction that will be done. So this is the test that we did this morning before the call, just to make sure everything was working. So just disregard this. There will be a new prediction coming a bit later. So again, we did these 3 parts. So what has happened in theory is that the ML model has been notified of the creation of a new ML processing. And then what it did is get the subscription query, so to understand where to get the data. And it has created a subscription to look at the change of these attributes. And so we can verify that. So I can check that the creation of a subscription by the consumer app has worked. So in theory, it should not work because, yes, it doesn't, because I'm not authorized at looking at an entity created by someone else. So that's the application creating this entity. So I'm not authorized to look at it, but I will be able to check the creation of a subscription to the input data. So here, that's a subscription to the information that the consumer application was provided. So a subscription to the to this entity, which is our river. and specifically to the property precipitation. So the subscription to this data has been created correctly by the ML model. What we can do now is simulate the update of the precipitation. So we have either an IoT device or a sensor that can update automatically in the context broker the precipitation information, and that will trigger the prediction. So basically, when the precipitation will be updated, the YAML model will be notified. Excuse me. Will be notified of this change, and it will perform the prediction through the YAML model and update the river entity, the property flow of the river property. So let's do this simulation of sensor. So I'm updating this river entity. So let's change this to, I don't know, so that 56.2 millimeter of rain. I'm sending the request to patch, so update this specific precipitation attribute of the entity, and we should be able. So what has happened here again is that part. So I updated this precipitation entity, notification, predict, and update of flow of the river entity. So on the app, we should have yes, 1023, yes. So we should have we have a prediction of 81.1 cubic meter per second in terms of flow. So we can check that that's really what's into the river entity. So I can do a get here. And yes, I have so my 62 that was in prediction, and 81.1 as oh, sorry, 62, which was the precipitation updated, and the prediction of 81 for the flow. So obviously we can also do it again. So let's do very heavy rain. Let's see what's going on with that rain. So yes, a very big flow as well, of course, and we can check into our consumer app. Yes, that we have the same information. So the consumer app has received the oops, sorry. So the consumer app is receiving the notification from directly from Stadio, from the context broker. And yeah, that's it for me on my side. So I can pass the next presentation to Anwar. Should I stop sharing then? Yes.
Yes, because I can share.
Okay. Okay, you're ready to go, I think.
Yes, just a second. Can you see my screen?
Yes, we can.
Okay, perfect. So I'm Anwar from EGM, and I'm specialized in video analysis using artificial intelligence. So Didier talked about machine learning as a service for time series using BentoML. And now I'm going to talk about the same approach, but for image analysis or video analysis. Can you see my slideshow?
Yes, we can.
Okay, perfect. So we're gonna take a real-life example and try to demonstrate this application using BentoML and our context broker. So we will take the example of social distancing in a video. So here we have our a street or a place. We have our image, and we have multiple people. And what we are trying to do is get statistics of social distancing based on these images or this video stream. Like, for example, we want to know the number of people in the scene, the number of groups of 2 people, the number of groups of 3, and so on. So there's multiple approaches to go about this. I'm going to talk about 2, just to demonstrate or explain the difference between that makes it more clear to see why we are using machine learning as a service. So the first approach is doing what we call machine learning on the edge. So basically, we have our street where we have a camera or video surveillance, and we put a processor next to that camera or in that environment, which will be running our deep learning model. And so it will receive our image directly from the camera, and it will be sending the detections to our context broker, which will be on the cloud. So there's a couple of things to notice here. The first one is that the image stays in this environment. It doesn't arrive in the FireWare cloud. So we have less control or less monitoring abilities over our model. We can't actually see if it's doing the right things or not. And another question we should be asking ourselves is: do we actually need this deep learning model to be running on the edge? Do we need it on the street, for example, in a different application where we need real-time results? Like, for example, if this processor needs to be attached for a door for some reason, and needs to open the door whenever it detects a person, then it would be counterproductive to send each image to the cloud and wait to receive a prediction to what the person is waiting for the door to open. So do we actually need this deep learning model to be running on the edge? In this case, no, because we are doing statistics and we don't need real-time results. We can store our images and process them whenever we need to. And the last thing we want to take into consideration is if we are not using this processor here, can we actually afford to send images to the cloud? Because images are not like time series data that comes out of temperature sensors, for example. Images are what you call heavy data. So if we are going to send a stream 24/7 to the cloud, we should be asking ourselves if we can afford to do it. So now the next approach is what we are talking about today, is machine learning as a service, which will be basically our camera on the street sending the images directly to our FireWare cloud, which will contain our deep learning model running over a BentoML service. And we will have a script that will do the link between the incoming images and the BIM2ML prediction service via API REST. So you send the image to the service and receive the detections, and from there it can send the detections to our context broker that we will later apply or use this context broker to get the results or the predictions in our consumer app. So this approach allows us to monitor our data. So because we were receiving our images in the cloud, so we can compare the images with the predictions of our model to see if how well is our model performing. And the second advantage of using such approach is scalability. So if we have multiple cameras from different places, we can use our model, the same model. If, for example, we are receiving images every 5 or 10 seconds, our model will not be doing anything for these seconds, so we can attach multiple cameras. So right now I'm going to demonstrate how to put all of this architecture or this approach into effect. Can you see my notebooks here?
Yes, we can.
Are they clear? Do I need to zoom in, or?
If you can zoom in, that would be nice.
All right. Better like that?
Yes, thank you.
Okay, perfect. So first, in this notebook, we suppose that our model is ready. We don't that we went through our phase training phase already, so we have our model ready. I'm going to use what we call a YOLO V4 object detector, which is one of the popular object detectors that allows real-time detections. And I'm using a YOLO V4 Onyx model, which is a public model trained on the COCO dataset. It's a model that allows to detect over 80 different objects, including people. Okay, this came out wrong. I didn't mean to say that people are objects, but yeah, you get the idea. So we find our model here, which is the Onyx model zoo. It contains multiple different models for different applications like image classification, object detection, and segmentation. YOLO V4, which is what does this type of which does object detection. So the model was so the notebook was taken from this the original one was taken from this model zoo. It comes with the model, and I'm going to run this model to get a sense of it on a particular image. So first we're going to read an image, which is this image, and we're going to apply pre-processing steps, which we need to do to get to so we can apply our images to our model, because the model actually expects an image of 416 resolution. So we need this pre-processing steps, which is basically resizing the image. After we've done that, we can run our model. On the image and get our detections. But this will output a lot of data, which isn't what we actually need. So we still have to do some post-processing steps to actually get the valuable information from the model output. So here we have a couple of post-processing functions that come with the model. So what these basically do is take the model output, which contains a lot of information that we don't need, and apply these functions to get what we actually expect of the model. So I won't go through them in detail, but just to visualize what this is used for is, for example, this post-processing step, which we call non-maximum suppression, takes an image of. So this is what our model has like an output. We can see it's a lot of data. It's the same detection, multiple detections for the same person in different probabilities in different locations. What this post-processing function does is it takes the highest probabilities for each object and outputs the detections that will most probably interest us. So after we've done that, we can start building our BentoML class. So there are a couple of important things to take into consideration here. The first one is our environment. So it's the packages we will be using. This function or this parameter allows automatic inference of the packages. So it will detect what is here and the versions, and will include this into our BentoML package. The second one is the artifacts, which are basically files that our BentoML function or BentoML class will be using. The first one is the model itself, of course, and the second one is the labels file, which we can see here. It's basically a file that tells the model what it's able to detect in words. So we can see here person, bicycle, car. It's up to 80 classes, like we've talked about before. So inside our class, we have to define our functions, which are basically the same functions that we ran in our notebook, our pre-processing steps and our post-processing steps. We've defined our functions here, and what's important is our predict function, which is the function that will be called each time we make a API post request. So we use this line to tell our class that this is the function that you should be calling, and it will receive an image in the as an input. And in this function, we run our pre-processing step. Then we run our inference, which we call basically calling our model, applying the image to it. And then the post-processing step, sorry, to send the bounding boxes, or what we call the detections, in the API REST request. So now that we've defined our function, we can go ahead and call it. So I changed. I should be okay. Oh, okay. Okay, I am not in the right directory. I'm just gonna call or survey the latest Bento ML model that I've created. So it's so I'll launch this command, which will start a server hosting our prediction function, which expects an image as input. So we can now send the images to this service and get the detections as an output. Then I've made a small script that will simulate our camera on the street. I've taken a live YouTube video of Times Square in New York, and we will try to run detections on it. So what this script basically does is it takes the video as input and loops over the frames and saves an image in a cache directory every 5 seconds. So every 5 seconds we will receive an image in our directory, which we can later process. Then I've prepared a script that will loop over the images in our directory, and will send the image to our prediction service, which will give us the detections, and we will use these detections to get statistics. We will use clustering algorithms to get statistics on this to get valuable informations from our detections. And once we get our statistics, we'll update our NGSILD entity, which we've defined as the following. The entity is what we call the square, which is a place, and it has some properties like the people number, how many groups of 2, groups of 3, and so on. So this will be updating our entity, and I've added a visualizing function to so we can see our images with our detections applied to it. So I'm going to run a demo. I don't think we will see many people on this right now, because it's like in the middle of the night in Times Square. But I've prepared a video to demonstrate more what this application does. So here we will go to our cache directory. We see the images arriving. Like I said, there's not much people. But we will run the script nevertheless, so we can see if it outputs something. So here, the first, I don't know where this is coming from. Can you hear this voice? Sorry. Okay. So we've run our detections here. We don't have any detections.
We lost your screen.
Oh, sorry.
No worries.
At what point?
Just now.
Okay. Okay. So okay. Can you see it now? Yes,
we can.
Okay. So I've run my script, and it outputs something like that. We don't. There's not people on the moment. There's one here, and there's a false detection here. This is basically a state show. But this demonstrates what we were talking about before. If we were running this, if our prediction was being ran on a processor on the street, we don't have access to this image, so we can't actually see what the model is doing. So this kind of stuff can happen. So it's always that's why running machine learning is a service is a good idea. So here we've got our model is basically detecting 3 people. We can see if we go on over here. We can see these detections arriving. I'll just change that. Okay. So we've got here our detections arriving. There's like we saw, there's 3 people, and there wasn't any groups. So groups are at 0. Now we have one person, which is basically the statue. So I'm going to turn this off. Turn this off and show you a video that was pre-recorded before, which we can see actually groups of people. So this was recorded yesterday. We've got some detections. Images are arriving every 5 seconds, and our model detecting the people, and this is doing some visualization to show the groups in the same color. So here we got a group of 3. We saw it over here, and we can see the people number. It's around 21 at first. Then what happened here is the camera actually zoomed out. So we have this drop in the number of persons, because when the camera zooms out, we have less resolution. It's the same resolution, but the people actually get smaller. So it's harder for us to detect. So yeah, this is what we prepared for this demo. I think I've covered most aspects of the cycle. So if you have any questions, we'll be more than happy to answer them. Thank you.
Thank you very much. What we will do is we will take all the questions at the end of the session. We're already addressing some in the chat. So before we move to the next presentation, I would like us to take a break for 10 minutes, and then we can continue. So let's come back at 11 a.m. to continue with the second part of the session. Thank you, everybody. And we're back from the break. And for this second part, we have 2 speakers, and we're going to start with Sharifa. So please go ahead.
Okay, thank you, Jane. I'm going to share my screen. Can you see it?
Yes, we can.
Okay. Great. Hi, everybody. I'm Sharifa Fayed. Perhaps you know me from hosting. I'm a technical expert and evangelist at Fireware, and I have here with me my colleague Rihab Faki, a machine learning engineer and evangelist. And today we want to present you a use case that we have been working on, which is an end-to-end AI solution with PySpark and real-time data processing using Apache NiFi. And what you hopefully can take away from this demo or this presentation is get an idea of how you can manage real-time data with the context broker and how to use Apache NiFi to perform data persistence and some data transformation operations. And you will also see how to set up a Google Cloud environment and the data prop cluster, and how to create a machine learning solution using Jupyter Notebook. And at the very end, we will give you an idea of phase 2, which we are currently working on, which is deploying of the model that we have created. Okay, so let's get into it. What you can see here is an end-to-end architecture of our solution powered by Fireware. You can think of it as consisting of two halves. So you have here this lower part, which deals with the acquisition and pre-processing of the data. And the second part is the upper half, which deals with the setup of the cloud environment in which we will create our AI solution. And let me start by explaining this part, which is how to get your data through the context broker into NiFi. But for that, let me give you a quick overview of NiFi. What is it? It's basically a system to process and distribute data. So perhaps you can see here in this image those boxes, which are so-called NiFi processors, and each of them does an operation like routing and transformation operations of data. And basically inside NiFi you can see the whole flow of the data from beginning to end in a web-based user interface. And the way that you connect your context broker to NiFi, or how we did it in this simple solution, is to run Dockerized images of NiFi and of your context broker and put them all on one network and make them communicate through exposed ports. And to dive into the example that we have, let me give you an idea of our entity. Since this is a bit from a project more on the industrial side or on the manufacturing side, our entity is a steel plate, and its attributes are geometric measurements of that steel plate. And with our model, we want to detect faults that can happen in the steel plate. And I can show you a little demo. So this is my NiFi setup. And here I have this first processor called listen HTTP. And what it does is it listens to notifications coming from the context broker about any changes happening in those attributes of the steel plate, which can come from something like sensors or IoT agents. And just to demonstrate, so our entity is okay. This is our steel plate entity. I've already created it, and it is here in NGSI v2 because it doesn't have an at context, but of course it can also be NGSI LD. I have posted it to our context broker, and I have created a subscription which notifies NiFi, and whenever a change happens, I will just induce some change now manually, but as I said, it would be coming from a sensor from the factory or something similar to that. It's not too slow. Okay, I go here and refresh, and yeah, this output has jumped from 0 to 1. If I want to look at it, I can see it here under the content of this file. Let me format it. Sometimes it doesn't work. I'll just quickly post it here. Sorry. Just so we can see if we indeed have gotten our new value. So the value I had assigned here was 43 to the attribute X minimum of the steel plate, which is one of the geometric values. And if I look here at this X minimum, yeah, here it is 43. So whatever has changed, I have received the full payload with the changed attribute. Let me go back. All right, so this means that now we have managed to get our updated entity into NiFi, and from there we can start performing the rest of the steps on this entity inside, or yeah, with the help of NiFi. And I'll now give the floor to Rehab to continue with the following steps. We need to stop sharing.
We see your screen, we just can't hear you, Rehab. We still can't hear you.
To me, it's showing that it's loading on
Loading.
the image, yeah. But in the backstage, we were able to hear her, so
perhaps leaving the Hermit and coming back.
Yeah. And if the internet connection is not stable, try a hotspot maybe.
She left, so I think she's gonna rejoin in a second.
Yeah.
So I'm back.
Yes, you're back.
Can you hear me right now?
Yes, we can.
Okay, perfect. So I'll be sharing the screen now. I hope that it's visible and that you can hear me as well.
Yes.
Okay.
We can see it.
Perfect. So yeah, hello everyone. My name is Rehab Vicky. I'm a machine learning engineer and evangelist at the Fireware Foundation, and I'll be walking you through the second part of this demo. So here we can see our data flow overview. We have seen with Sharifa how we could get the data in real time, ingest it through the context broker, and be able to read it in NiFi, so that here we can do the processing and the data persistence of the incoming new data. And then our next target is to store the resulting data set in a Google Cloud storage bucket. Then this persisted data set will be used to train machine learning model in Dataproc, which is a cloud service. And I will be going through the details of it in later stages. But for now, I'll be focusing on this part. So I will be zooming into this box to know what is happening in NiFi. Yeah. So here, this is a simulation of NiFi. Our target is to convert our NGSI LD files to CSV, and this processor will be triggered each time we have new incoming NGSI LD data. Then our target is to also collect a data set with, for example, 10,000 observations, then merge all of the resulting CSVs into one aggregated data set. So, and this is something which we can configure in the merge processor by setting the minimum number of observations we need to have. Later on, after having this data set, we will use the put Google Cloud storage object processor to be able to store it in the Google Cloud storage bucket, after, of course, having credentials for that. So here is the overall NiFi workflow. I'll be showing a demo on the different process. But before that, I would like to explain to you each of these processors' functions and what they serve for. So we have used here the listen HTTP and the get file processor to get the data. So the listen HTTP is what you have seen already with Sharifa. We had configured it to listen to any notification which is received from the context broker. But for the demo purposes, I'll be using this processor get file to get data from my local machine, which is also in NGSI LD format. Then I'll be using this processor called Jolt Transform JSON, which will apply transformation on our incoming JSON LD data, which is nested, so that we can transform it into a simple key value JSON. Later, the output of this processor will be converted to a CSV. So using the convert record processor, and after that, I'll be using the merge content processor to merge all the resulting CSVs into one file. And later on, I'll be using the put Google Cloud storage object so that I can save this data set in Google Cloud. Okay, in the presentation, you will find a detailed description of the different processors. So let me switch now to NiFi. So here I have deployed container of NiFi, and I can also show you. So yeah, so this is my YAML file. I have here an image of NiFi, and I have in my volumes so the data, and this is the data I'll be using. I have 3 files of steel plates, and I will show you an example of yeah, the data model which we're using. So it is in this format, and later on we would like to predict so the yeah, the fault of these steel plates based on the different attributes or entities. Okay, let me get back to NiFi again. So I'll be starting each of these processors that we can see the queue each time. So, and I will get also to the configuration of each of these processors that you also can understand how does it work. So for the get file, I have here to precise my input directory. So this is the path to my NGSI LD data, which you have seen already. And one important parameter as well you can use is the batch size, so how many files you can read at the same time. And besides other yeah, parameters you can use. So I'll start it. Yeah, so we have here in the queue the 3 files that we have read. Here's the queue. I will just show you an example, but yeah, how it looks like here. So these are my this is my input data. It is in JSON LD format. Then I will use this processor to apply the transformation on it. So, and I can show you which, yeah, so here I said this processor used the Jolt specification so that you can do transformation on the nested JSON, that you can make it later into a simple JSON. So, yeah, I have listed here my operations. So it's basically shifting some, yeah, so key values in the right place, how I want it, and then I will show you what is the result. Okay, so see this one, for example. So here I have my resulting JSON file. So you can see that it's a simple key value. So it was nested, and now it is much more simpler to transform this into a CSV than, yeah, going straight forward from the initial JSON file. Okay, once we have done that, the next step will be to get these values together in a CSV. So, and for that, I will use the JSON to CSV convert record. And for it, I have to use a record reader. And here I'm using a JSON tree reader since our input data is in JSON format. And since we want our output to be a CSV record, then for record writer, I chose a CSV record set writer. And yeah, you just have to configure both of them, and yeah, so to get your results. I will be running this processor right now to see the results. So we have in our queue 3 resulting files. See them? Yes. So here we have we can see the different values extracted from our JSON, and they are separated by a comma. Same for the others. Okay, so this process will repeat until we get, for example, 10,000, for example, queued CSVs. So, and this is what we need to do in the merge content processor. And this is what I'm talking about here. So it's the maximum, so the minimum numbers of entries. Since here I have 3, so I put it to 2, but so you can repeat this process until you say, okay, I want here 10,000 observation or CSV, that I can start to merge them all together. So, yeah. And I have also listed here the header for my CSV. And yeah, so this will enable me to get my resulting merged data set. So I will run this processor so that you can see the results. So here we have in the merged Q1 CSV. So, and we can see how it looks like. So right now I have succeeded to transform my JSON LD data to a CSV. Yeah. Later on, this is what we are going to use to train our models. But before that, since I'm doing the machine learning in the cloud, I would like to store my data in the cloud. So I'm using this processor. We'll show you its configuration. So what I have to do is here precise my project ID and the Google Cloud Platform, so which I have created previously. And you have to get the credentials to access the Google Cloud Storage service. And once you have done that, you also have to precise the bucket. So I have also created a bucket in my Google Cloud Storage service, and this is its name. And here I precise the name for my file. So this is the file which we will see later in my Google Cloud Storage. And its content is a CSV. So once I have that configured, I will run it. So, okay, then it was successful, and we can go now to the Google Cloud platform. And yeah, I will check the Google Cloud Storage. This is the service that I'm using to store my data set. Okay, so this is the bucket that I have created for my project. And inside it, I should get my steel plates data. So it has been received, and yeah, just right now. So, and then I'm gonna use this data to train my models in the cloud. Okay. So we have seen right now how to get the data through the context broker, apply the transformation on this data, and be able to persist incoming data from the context broker into Google Cloud Storage. Now the second part will be focused on our machine learning model creation, and here I have my machine learning environment. So I'm using Dataprog to create a cluster which has PySpark pre-installed in it, and also it allows me to also integrate Jupyter Notebook to my cluster using the Apache Knox component. And once I configure my cluster, I can access my Jupyter Notebook and create my machine learning model. And here I read my data from the cloud storage bucket using Spark data frames. And yeah, after training my model, I'll be saving it in a Google Cloud Storage notebooks bucket. So yeah, I will be going in detail to show the different steps on this part. But before that, let's know what PySpark is. So it is an interface for Apache Spark in Python, and it's a language for performing exploratory data analysis at scale, building machine learning pipelines, and also creating ETLs for data platform. And I'm using it to create my machine learning model. So it's going to be based on PySpark libraries. And yeah, also something else I want to explain here is the cloud data proc. So what it is, it's a managed Spark and Hadoop service that lets you take advantage of open source data tools for batch processing, querying, and streaming, as well as big data processing and machine learning. So why I chose Dataproc? So first, it's a managed service, so there's no need for a system administrator to set it up. It is fast, so to create a cluster, it takes you around 19 seconds. It is cheaper than building your own cluster, since you can start it and stop it whenever you don't need to run the cluster. And one more advantage is that it's integrated with other Google Cloud services like Google Storage, BigQuery, and Cloud Table, and it's easy to get data into and out of it. So so what makes it special? So in typical modes of operation of Hadoop and Spark, we basically start by deploying a cluster, then submitting the jobs to that cluster. But this method is not scalable, since whenever we need, for example, to submit more jobs or we need more computing power, we need to reconfigure our cluster again. And this needs time and resources. But this is not the case with Dataproc, since here you can submit a job to an already deployed cluster, and and once you submit that job, it creates a cluster on demand. Here you can see that it fits exactly the submitted jobs, so the cluster now is a mean to an end for job execution, and this method is now scalable. And since data scientists are big fans of Jupyter notebooks, but sometimes setting an Apache Spark cluster with the Jupyter notebook can be complicated. Let's see how it is easy and scalable with Dataproc. So this is the overall architecture of Apache Spark and Jupyter Lab architecture on Google Cloud. We have here the different data sources. So in our case, we're using only Google Cloud Storage, but in big data cases, you can use the BigQuery Storage API and other services. And so how does it work? What you need to do? It's some simple steps. First, you need to set the cloud environment and create a project. And then, you need to create a storage bucket for the cluster. Here you will save your data, the jobs output, and so it's necessary. And it's a step you need to do before creating a cluster. Then we proceed to create a cluster, and we will use some additional component to it, like Jupyter, and by enabling something called Component Gateway. Then we will access the Jupyter Lab web UI and create our notebook and develop our machine learning algorithm. Here, there are two ways to create a Dataproc cluster. The first way is using the Cloud Shell. I want to explain here this command to be able to create it. So you just, precise your cluster name, you give the region, so the closest to you, and you precise the master machine and the worker and their types as well as the numbers. And you can choose, there's a guide to choose well the master and worker machine capacities. Then you precise the bucket, and here the optional components which I want to pre-install in my cluster once it is created. This is something so important because you have to set your cluster before you create it. Later on, you can't really add other things to it, or frameworks or so. So you have to do it at the beginning. And this is by enabling the component gateway that you can add new components to it. And I'll be adding Anaconda and Jupyter. Yeah. And the other way is to use the graphical user interface. So you just have to fill a form. And this is what I mean by enabling the component gateway. So, and you have other optional components which you can add, like Zeppelin notebook, Docker, Flink, HBase, and so on. So, okay, one more step before we get into the explaining how our machine learning creation steps. So we have a data set in a CSV format, and we have around 2,000 samples. So our features are geometric measurements of the steel plates, and what we are trying to predict is 7 fault types of these steel plates, which can be pastry, scratches, stains, dirtiness, and so on. So now I'll be giving a demo how to set the cloud environment, and later on the modeling of the ML solution based on PySpark. So if you go to Dataprog here in this entry, I have already created my cluster, but as I showed earlier, you can create it through a form by a simple click here, or using the Cloud Shell by submitting this command that I have explained earlier. So my cluster is created and it's running. And let's see. Now what we need to do, we have here different entries. So to see the jobs and how many the VM instances and the master and the jobs and the workers which we have in our cluster. But what we will be interested in today is the web interfaces. And from here, I can access my Jupyter lab. So okay, so now I have my Jupyter notebook, and it's based on PySpark. So first, what I have done is creating PySpark session, and gave it the name, and imported the different libraries which I'm going to be using in this to create this machine learning model. I imported here my data, so from my Google Cloud Storage bucket, and this is the link to it. Yeah, once I have imported, I can see here my PySpark data frame, and what we are going to predict is this target. which represent the different steel faults. I have done here some exploratory data analysis, checked some missing values in my data frame, and yeah, have done some analysis on my target classes. So we can see here the data set is more or less unbalanced. So we have for some classes, yeah, less than 10% to 5%, and for others, yeah, bigger the distribution. So this might affect our machine learning model later. Yeah, something specific to PySpark is that when you train your model, you have to list all the features into a vector. So I have all my features here, and I need to store them all in an array. And yeah, and that is using the vector assembler library. And later on, what I did is, yeah, okay, so I can show you also how it looks like. So the row features. Here, all my features right here are in an array. But before I will be starting the training, I need to scale these features. So I'm using the standard scaler library of PySpark, and I have my features scaled as well in a vector, which I'll be using to yeah, train my model. One last step is to encode our target, since it's a categorical object. So I will use a string indexer to, yeah, transform it into an integer. And yeah, I have here my corresponding labels for my my target data. Later on, I'll be doing the train test split. So I have my features, I have my label, and yeah, I will use 70% for training, 30% for the testing. I will use cross validation and param grid to figure out the best model. And for this purpose, yeah, for our classification, I'm using random forest classifier. And yeah, after running the param grid, I can, yeah, I get the best model, and I can fit my training data to it and then test it. I have also here saved my trained model in a Google Cloud Storage bucket, so I can find them here under my this folder called PySpark models. And later on, I can see the predictions, which gives me, yeah, so the features I've used, the row prediction, the probability for each class, and yeah, but we can be interested in only seeing the prediction corresponding to, yeah, here is our actual label, and this is what my model has predicted. Later on, we can see our model evaluation. I used F1 score because it's more useful than accuracy, since we're dealing with an unbalanced data set. I have a score of 75%, so it is quite good. And with PySpark, you can also use have access to confusion metrics for each class, how it performed, as well as other metrics like precision, recall, F1 score for each class. So yeah, and we can see here for some classes I have reached 90%, and for some others it's around 60 to 70%. So this is due to the imbalance of the data. Yeah. This is basically it. So we have seen how to create the PySpark machine learning model, and yeah. So next, I will hand over to my colleague to walk you through the steps of the model deployment with Flask. So
I think you can stay on the slide.
Okay, yeah.
Yeah, thanks a lot for presenting. Now, after Rehab has created the model and saved it, what we want to do is actually deploy it. So this is the part that we're currently working on, and the architecture of our solution is to also use Dockerized images of the context broker and create a server using Flask and a Python script. Exactly. And through this Flask app, we want to get data from the context broker into our Python script, save it there as a variable, and from there bring it to the model. And then the arrows, is it loading just for me? And I don't know, I don't see the slide anymore. Is that just me? Maybe I have got it.
I also don't see it. I don't know. So did I stop sharing or so?
Maybe it's fine. I can share.
Okay.
Do you see it? It's still loading. Now?
Yeah.
Okay, perfect. So yeah, as I said, and once we have our prediction, we can go back through our Flask app and update with it the context broker. It's a bit similar, I think, to what we have seen from EGM. And yeah, we plan to have finished this part by summer, so by beginning of summer. And that is it. We have compiled some useful links for you. You can see the source code and documentation of the work on this repo, and also, but I think we will also upload it in the one where most of the, or all of the trainers code is at. You can also see the notebooks that Rehab has presented, and also the NiFi documentation, a bit more details about what happens in every processor you can see here, and some other useful links. For example, the one that helped me with creating the Flask app and Dockerizing it. To sum up, the context broker does not store data or persist it. To do so, you need something like Apache NiFi. And the Google Cloud Data Proc service provides an easy and fast way to set up data science environments, but also it has its drawbacks. For example, that you have to install additional dependencies and libraries up front. So after you have created it, it's not possible to add any anymore. And also it's limited to some programming languages, but yeah, if yours works with it, then it's a great solution. And Apache NiFi may seem complicated, but it's a very powerful tool to manage big data flows and automate them. Yeah, and is very good for dealing with large-scale data and real-time data. And of course, you can also use other cloud platforms like AWS or Azure. Doesn't have to be our solution. And that is it. Thank you very much. And let us know if you have any questions. Okay, I have one question actually. I think it's to Didier. When the part where you subscribe to the context broker, where do you send the notification to in your Jupyter Notebook script?
Can you repeat the question, please?
In the part where you subscribe to the context broker, you usually send the notification to a certain link. Where do you
so yeah. There was two different subscription from two different actors. So one was the basically the model subscribing to new update of property precipitation from the rain from a river entity. Sorry, and in that case, the notification is going to the ML model, so the Bento ML Docker basically, and the second one is the notification to the application consumer. This is also going to this application. The notification when the prediction is updated, a notification is sent by the context broker to the consumer application.
Okay, yeah, I'm asking because the solution we thought of was creating this server with Flask. So I wanted to understand your alternative, but yeah, okay, then it's Bento ML or the consumer application itself. Okay. If anybody has any other questions, you can either post them in the questions section or you can raise your hand if you want to talk.
This is Rehab, so I have asked 2 questions to Anwar, and yeah, maybe I should speak them out loud right now that everybody could make use of it. So I have asked him how could the solution he proposed, leading with images, could be scalable, because he have showed how to get the images through the camera and then run the scripts, a Python script which sends it to the cloud. So what my question is here is, do you use any streaming framework, or what is exactly in this script?
So in this script, just let me. I've used a library, Python library, which is Streamlink. It allows us to stream a video from a URL. So this is what I use here, but that's I don't think it's the most optimized for a video stream. Like in other like here, I've used a YouTube video because like I didn't have access to a specific camera where I can stream the video directly, but I believe it's depending on the protocol, the streaming protocol. We can there's specific libraries for that with difference with better performances. But yeah, the performances I got from this library from a YouTube live YouTube video wasn't particularly the best. Like sometimes we see the video moving fastly, the frames moving fastly, then it stops a bit, then it moves fast again. So yeah, but yeah. Did I answer your question? Or just,
kind of, but I also had this like a question before, and I don't know if you know about Flink. So it also.
No, I don't actually. Well, it's we're talking about what?
The image streaming, so, or video. It's I can put the link to it. Maybe you can learn about, just to enhance maybe the solution, also to make it scalable. So it's a stream processing and batch processing framework, but mostly for stream processing. So it could be ideal when you have images or videos to use it.
Okay, thank you for the information. I will look it up for sure. You sent the link. I don't see it. It's in the
I don't
chat.
know if I should put it in open questions. I will put it in open questions.
Okay, perfect. Thank you.
Mm-hmm.